Okay. We're going to go over this later in the course and more practical aspects of biochemistry, but just to remind you where these values actually come from. How do you measure thermodynamic parameters? Well, delta G is, again, directly calculable from an equilibrium constant. We won't worry about things like standard states, that these are delta G's are reported at 1 molar concentration, given temperature. But the key idea, of course, is that if, let's say, you have a macromolecule binding to a ligand, the equilibrium constant K will just be the concentration of the ligand macromolecule complex divided by the concentration of the free macromolecule divided and the free ligand concentration. Okay. Now, where do we get this from? Okay. Well, there are various ways. Equilibrium dialysis is one way. Equilibrium sedimentation, surface plasma and resonance for protein-protein interactions. Some change in a spectroscopic property upon binding, like intrinsic tryptophan fluorescence changes. We'll be going through this later in the class. What I want to emphasize, though, is that all these methods require knowing these concentrations accurately. And this means that when people do things like pull-downs, which is very common, as many of you know, these are really not well-controlled experiments because you don't know the actual input concentration. So it's something that's important to keep in mind. Now, we can get the enthalpy of these reactions from the equilibrium constant if the delta H is independent of temperature. And this is something you learned about in freshman chemistry, the Van Hoff equation, that if we measure the equilibrium constant at different temperatures, we can then obtain the delta H of the reaction. And if we have that, then we can simply get delta S from the delta G we got from the equilibrium constant and the delta H from this temperature dependence of the equilibrium constant. So we can get all these quantities that way. Now, what we normally do when we talk about affinity, just because the concentration is similar, is we usually talk about dissociation constants. So we turn the equation around and say that the protein ligand complex dissociates into free protein and free ligand. The KD is that, and those units are molar, so they're just easier to work with. Now, in a real reaction, in an experiment, we'd only know the total amount of material that we add, and then we let it equilibrate. So it's very convenient experimentally to define occupancy or the fractional saturation of the macromolecule by the ligand. Okay, and that is simply the concentration of the ligand macromolecule complex divided by the total input macromolecule. Okay, and that, of course, is going to be the concentration of the free ligand plus the concentration of the complex, and that reduces to just 1 over 1 plus the KD divided by the ligand concentration. Now, we assume here that the ligand concentration was much larger than the macromolecule concentration, so that we can ignore the free versus difference between free and total ligand concentration in that case. Okay, so if we measure the fractional occupancy as a function of the ligand concentration, we can get a very simple KD from that, and that's what you often see. And that's going to be, the KD is going to be the concentration of ligand at which it's half saturated, and often it's plotted on a log scale because it's this is a very common way. It's often called a Langmuir binding curve, Langmuir binding isotherm at a given temperature. Okay, now I just want to end this by mentioning there is another way of getting enthalpy directly in a method called isothermal titration calorimetry, and this is actually a very powerful method because it as I'll show you, it exploits some very basic thermodynamics without any assumptions. The basic idea is that you're measuring the heat change when you add a small amount of one reactant into another. So you titrate the ligand into let's say our protein, until we get no more heat change, until it saturates. Okay, so if you look up down here, we're just putting the ligand in at some concentration and we're watching the heat change and eventually it saturates. So what happens in this procedure is that we maintain the sample at a constant temperature and we inject a small amount of the ligand and it's stirred to ensure it mixes rapidly. And we can measure the amount of heat that's required to maintain the sample at constant temperature. So in other words, there's a heat release or absorption each time you add some ligand, and the electronics of these instruments basically maintain the sample at a constant temperature, and they can measure how much heat was needed to do that. And that's what these plots are, okay? As you titrate in the ligand, this is telling you how much power the instrument had to do to maintain the temperature. So at a given concentration of ligand, the fraction that's bound is going to be related to the equilibrium constant, and basically that allows you, as you generate one of these curves, you can get both the you can get the equilibrium constant, therefore the delta G, and the total amount of heat that had to be added to saturation is, when you integrate all these little heats, that's the delta H of the reaction. And so you can then fit these curves with the delta H, the K, again that gives you delta G, and therefore those two give you delta S and the stoichiometry, it turns out. Okay, so this is a sort of, in a way, it's a gold standard method because it is a direct readout of delta H. There's no assumption about the temperature dependence, like the Van Hoff equation. There's no assumptions about spectroscopic readout because you really are directly measuring the heat of the reaction. It's extremely accurate, particularly if you know the stoichiometry from other studies. The big disadvantage is that it requires a huge amount of material, so you can't always do this, and it requires well-behaved material. And it does depend on measuring heat changes, so if you have a more or less isoenthalpic reaction, that's really an entropy-driven one, it can be very hard to get accurate data. And it turns out it's very hard to get data from weak interactions, just the signal's not very big. But and at very high concentrations, it can be hard to measure. But despite these, this is a very important method for getting accurate thermodynamic parameters in biochemistry.